Hello to everyone out there in isolation land. Today we're going to take a look at day 5 for geometry. And we're going to specifically look at section 8.2.1 classwork. And that is numbers 67 through 70. So here we go with number 67, the Mighty Mascot. To celebrate the victory of your school's championship girls ice hockey team, the student body has decided to hang a giant flag with your school's mascot on the gym wall. To help design the flag, your friend Archie has created a scale version of the flag measuring 1 foot wide by 5 feet tall. So that's going to be the smaller one here. So we have 1 foot wide and we have 1.5 feet tall. The student body thinks the flag should be 3 feet tall. How wide would this enlarged flag be? So if we were to take and extend the height of this to be 3 feet now, that means I would have to double the height of the flag. To make this side be proportionate, I would also have to double this side of the flag. So if it starts off as 1 unit, then it'll be 2 units. So the answer is it will be 2 feet. If Archie used $2 worth of cloth to create his scale model, then how much would the cloth cost for the full-size flag? We're going to actually come back to this question in the next one, so I'm going to leave that blank for now, but you might want to go back in just a minute and fill that in. But think to yourself, take a guess. What do you think that cost would be? In order to figure out the cost of the flag, what we need to do is see what the comparison is of the areas. In other words, we know that the height and width are each twice as big, but does that mean the area is twice as big? To figure that out, what we're going to do is we're going to go ahead and take each of these little triangles. So this triangle is the same area as the original flag, and I'm just going to cover up the new flag, the enlargement, and see how many of these small triangles it takes to fill it up. When I do that, you're going to see that it actually takes 1, 2, 3, 4 of the small flags to fill up the area of the new big flag. So it takes up 4 of them. Does this confirm your answer for part B? Well, it depends what you put in for your answer for part B. And then it says, if not, what will the cloth cost for the flag? Well, if it is 4 times bigger, then it's going to cost 4 times as much. So we take 4 times $2, which was the cost of the cloth for the original, and we end up with $8. So the cost should be $8 for the enlarged flag. Now what happens if instead of being twice as big, or in other words, twice as high and twice as wide, then what happens to the area? So we're going to do the same thing we just did in the previous one by taking triangles and moving them over this flag and counting how many of these triangles does it take. So if we're doing this, whoops, put that back there. You can see that now when you made it 3 times as wide and 3 times as tall, it's going to take 9 of those smaller flags. So because it takes 9 of the smaller flags, we have to take 9 times $2, which will give us $18 for the cost of the flag that is 3 times as big. And now let's see what happens if we do it when it's 4 times as big. So again, we're going to line up these flags. Again, each of these triangles is the size of the original, and this one is 4 times as wide and 4 times as tall. So maybe by now you can guess how many there are going to be. And let's go ahead and count them. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 of them there, and that means that the cost of the cloth will be 16 times the original, so that will be $32. So let's just kind of look at this and analyze this a little bit. We have two different types of ratios here. We have what we call a linear ratio, which I'm going to abbreviate LR, and we have an area ratio, which I'm going to abbreviate AR. Now, when I'm talking about the linear ratio, what I'm saying is, what is the length of one side compared to the length of the other? So, for the very first one, we said that the linear ratio, is going to equal 1 over 2, because the second flag was twice as big as the first one, which made the area ratio 1 over 4, because 4 of those flags fit into one big one. The next one we did when we had a linear ratio of 1 over 3, because the second flag was 3 times as long and 3 times as wide, we said the area ratio was 1 over 9. And the last one we just did, the linear ratio would be 1 over 4, because the second flag was 4 times as big as the original, and the area ratio was 1 over 16. Now, let's just compare these numbers for a second. If I go from 2 to 4, and when I'm doing that, I'm just taking the denominators here and comparing them. And here, I'm going to go from 3 to 9. And then from here, I'm going to go from 4 to 16. Some of you might have seen the pattern here. If you take the linear ratio and you square it, you get the area ratio. And that's true for any shape. Anytime you take the linear ratio, you square it to get the area ratio. Okay, in number 68, we're going to do the reverse this time. In this case, we're going to take the area of one shape and say that it is 160 times larger than the area of a similar shape. So in this case, I'm given the area ratio. Since it's 169 times the area, the ratio would be 1 over 169. What it's asking me for is to find the ratio of the corresponding sides. That is the linear ratio. So if we say we have to square the linear ratio to get the area ratio, that means if we have the area ratio, we need to square root the linear ratio in order to get we have to square root the area ratio to get the linear ratio. So we take the square root. When you take the square root of a fraction, you can take the square root of the top and then the square root of the bottom. So in this case, that would be 1 over 13. Now remember that when you're doing these problems, this number up here, this 169, might be different for you. So don't just put in 1 over 13 as your answer, because you have to make sure you set it up as a fraction and you do the square root of whatever your number is. The next question says, if the linear scale factor is r, then how many times larger is the area of the new shape? Well, in this case, if we have the linear ratio is equal to r, we have to square that to find the area ratio. So my answer here is just going to be r squared. Okay, in problem 8-69, we're going to use both linear and area ratios to solve this problem. So to start with, let's look at what we have for a linear ratio. It says a linear scale factor or zoom factor is 8. So that means my linear ratio is going to be 1 over 8. To find my area ratio, that means what I have to do is square my linear ratio. So that will be 1 over 64. So I have an area ratio of 1 over 64. Now in this case, I need to solve this problem using that. I'm going to do that by setting up a proportion. So 1 over 64. Now remember, this is small shape, so the 1 goes with the 77 over the big shape. So that's going to be x millimeters squared is what I'm trying to find. So if we have a ratio of 1 over 64, the small area has to go on top, the big area goes on bottom. And when you do that, you're going to have to cross multiply, and you get x is equal to, so I multiply 1 times x to get x, 64 times 77 is equal to 4928. So that will be my answer here. And as far as the units goes, this will be millimeters squared. So again, in this problem, we're going to take a look at both the linear and area ratios. Remember that linear is basically a measurement you can take with a tape measure or a ruler. You're measuring the distance from one point to another. In this case, the larger one is 60 and the smaller one is 6. So my linear ratio is going to equal 6 over 60. When I reduce that fraction, it'll equal 1 over 10. Now, to find my area ratio, all I need to do is square my linear ratio, so that will be 1 over 100. Once I have the area ratio, I can set up a proportion. Now remember, 1 is smaller than 100, so the 1 goes with the small figure, the 100 goes with the big figure. In this case, I'm given the area of the big figure, and I want to find the area in the small figure. So I do 1 over 100 equals x, because that's with my small figure, over 1100. When we cross multiply, I get 100x equals 1100, divide by 100, and I get that x is equal to 11. So to answer the question, the linear scale factor is 1 over 10, and the area of the smaller figure is 11. And again, this will be my units, millimeters squared. Okay, in this question, the first thing is asking is that, is the shaded rectangle similar to the large rectangle? And we can figure that out. In order to do similar figures, two things have to be true. We have to have that the angles are all the same measure. Well, in this case, all of these are 90-degree angles, so the corresponding angles are all congruent. We also have to have the same ratio of the corresponding sides. If we look at the top, 2 out of 3 of these are shaded, and on the side again, 2 out of 3 of them are shaded. So the ratio of the corresponding sides are the same. That means that yes, they are similar. Now I'm going to erase this so we can see this a little bit better to do the next problem. So next one says, if so, what is the linear scale factor? Well, we just wrote that down. That's going to be 2 over 3. And what is the ratio of the areas? The ratio of the areas, well, there are 4 shaded blocks out of 5, 6, 7, 8, 9 total. So that would be 4 out of 9. Okay, so the next question says, while ordering carpet for his rectangular office, Trin was told by the salesperson that a 20-foot by 20-foot piece of carpet costs $400. Trin then realized that he read his measurements wrong and the office is actually 10 feet by 10 feet. Oh, that's no problem, said the salesperson. That is half the size and will cost $200 instead. Decide what the price should be. Okay, well, let's take a look at it. If we look at the lengths of the sides, my linear ratio, or LR as I abbreviate it, is going to be 10 over 20. That will reduce to 1/2. That means my area ratio is going to be 1 over 2 squared, which is equal to 1/4. If the area ratio is 1/4, and we're assuming that the cost of the carpet is based on area, then if the original one was $400, we can set up a proportion. So the area ratio is 1 over 4. Again, remember, this is small over big. So that we have the small rug is the new one. That's what I'm looking for. That's X. And the cost of the big rug was the original cost. So that's 400. So when we cross multiply, I get 4x equals 400, divide by 4, and I get x equals 100. So is it fair? No, it's not. And then what should the price be? The price should just be 100. Okay, and this question says, if the side length of a hexagon triples, how does the area increase? First, make a prediction using your pattern from problem 8-68. Then confirm your prediction by calculating and comparing the areas of the two hexagons shown at right. The area of the larger hexagon will be how many times bigger? Well, according to the pattern, if we say my linear ratio is equal to 1 over 3, that means that the length of the side of my new one is 3 times the length of the side of the original. That means my area ratio should be 1 over 3 squared, which is 1 over 9. That means that the new one will be 9 times bigger than the original. So let's go ahead and put these numbers in and see if that actually works out. Let's start with the smaller hexagon. So I'm going to take that triangle, I'm going to bring it out and put it here. There's the height and the base. Because I'm given the base, which is 15, because this is an isosceles triangle, that gets cut in half, which means that will be 7.5 and that will be 7.5. To find the height, I'm going to have to use some trig. So let's go over to our steps and let's start with step number 1. Step number 1 is to find the central angle. To find the central angle, all we need to do is take 360 divided by the number of sides, and that will give me 60. So my central angle is 60. Step 2 is to take half of my central angle, so half of 60 is going to equal 30. That is this angle right in there. So now we can set up our trig problem. The height of the triangle. Well, to find the height, I'm going to have to say that the tangent of 7.5. Now, I'm going to go back over to my diagram for a second. This is the opposite side, this is the adjacent side. Tangent is opposite over adjacent, which is why we're using tangent. But I have to get rid of this 7.5 there because it's actually the tangent of 30 is equal to the opposite, which is 7.5 over the adjacent, which is the height. Now, in order to solve this, this is a division problem, so h is equal to 7.5 divided by the tangent of 30. Now when you do this, make sure you go 4 decimal places. And when you go 4 decimal places here, you're going to end up with a height of 12.9904. To find the base was given to us in the problem over here, so the base is just 15. Next, we have to look at the area of one triangle. To find the area of one triangle, the area is equal to base times height divided by 2. In this case, my base is 15. My height is 12.9904 divided by 2. Again, I'm going to want to go 4 decimal places here. When I do that, I end up with 97.4279. And then lastly, the last step is to find the area of the polygon. So I take the number of sides, which is 6, times the area of one triangle, 97.4279. And this time I can round it to 2 decimal places, but that will give me 584.57. So that's going to be the area of my small triangle. So we found the area of the small hexagon is 584.57. Now let's find the area of the large hexagon. So again, I'm going to make one triangle here, draw that over here, draw in the height. Now in this case, my base is 45, which means each side over here is 22.5, and again, I need to find the height. So just like before, we have to find the central angle, which is 360 divided by 6, which equals 60. Then we need to find half of the central angle. So half of 60 is equal to 30. That angle goes in here. To find the height, we're going to use tangent again. So we have the tangent of 30 is equal to the opposite side over the adjacent side. So height is going to equal 22.5 divided by the tangent of 30. When you round that to 4 decimal places, you end up with 38.9711. So to find the base of the triangle then, the base, again, is just going to be the length of one of the sides. To find the area of one triangle, base times height divided by 2. So that's going to be 45 times 38.9711 divided by 2, and that number is 876.8507. and then multiply that by the number of sides for the last step, and you get 6 times 876.8507. And when you put that in, you're going to end up with 5,261.10. Now, originally the question asked us up here, the area of the large hexagon will be how many times bigger? Well, let's figure that out by putting it in as a ratio. So if we said the small hexagon is 584.57, divide that by the large hexagon, which is 5261.10, and you'll get something like 8.99995. Now, it's not exactly 9 because of rounding that we've done along the way, but if you did everything without rounding, it would be exactly 9, and this is very close to that and would round up to 9. So we verified that it would be 9 times bigger.